Hello and welcome. My name is Stefan Schaufler. I'm one of the product architects of the Leica GS18 I, and in this presentation I want to talk a little bit about the technology behind the Leica GS18 I. The goal of this presentation is that you get a little bit a deeper understanding about the algorithm and the technology of the GS18 I, whereby we will ask ourselves the question about how to get to globally referenced images and the technique behind how we can perform measurements in images. Finally, I also want to show some accuracy results from the performance tests, so that you get a feeling about the expected position quality of this visual positioning system. So our motivation is to support the surveyor to do the job better and faster. One big pain point in GNSS surveying was to level the surveying pole. I hope many of you know already now the Leica GS18 I. With this device, we already solved this problem. So we enabled tilt compensation. So with this innovation, it was not needed anymore to level the pole to take measurements. It was now possible to measure points from any tilt angle. So this innovation already speeded up the whole surveying workflow and increased the productivity. So how can we do this? In the Leica GS18 I, we included an additional positioning sensor, a so-called IMU, inertial measurement unit. And the algorithm in the GS18 I combines the GNSS measurements and the IMU measurements and computes the position and the orientation of the sensor in real time. And this information we can use then to enable tilt-compensated pole tip positions. So the surveyor can now save time at each measurement because holding the pole vertical is not needed anymore. In the Leica GS18 I, we included now another sensor, a camera. So the Leica GS18 I combines now GNSS data, IMU data, and now also camera data. This multi-sensor system enables now an innovative new workflow to measure points. And this novel workflow I want to show you now in a short animation. So just imagine you want to measure the corner of this building. Because this point is below a balcony, so you cannot measure it directly with GNSS RTK because you don't get the high precision position there because of signal shadowing. With the Leica GS18 I, we would just pass by the scene and we'll capture images. So we collect a group of images from the same object, in our case from the building corner, from different perspectives. So now the user only selects one image and selects the point of interest, in our case the building corner. And the algorithm in the GS18 I automatically detects the same position in all of the other images. If you have knowledge of the object point in all of these images, we can use photogrammetric forward intersection to compute the coordinates of the object point. So we measure the point remotely. This workflow brings us now some benefits. So as showed in the example before, with the GS18 I, we extend the workflow, the working range of a GNSS receiver, because we can now measure points in areas which were previously not easy to measure because we cannot get a high precision position with RTK there. Also, because we capture now the whole scene at once, we can measure hundreds of points within minutes. Or just imagine a busy road. You can now measure points across the street from a safe distance without stopping the traffic, closing the road, or bringing yourself in danger. You can now capture everything what you want, and you can decide later what you want to measure. So the key technology of this workflow are globally referenced images. So now let's switch to the technical part. How do we get to globally referenced images? So let's have a look at the workflow again. In this example, the surveyor passes from left to right and captures images. In these images, we want to take the measurements. These images, when they're recorded, they are somewhere located or orientated in space. The goal is now to determine the exact position and the orientation of all of these images. The position and the orientation of an image is also called camera pose. So we need to determine the camera pose for all of these captured images. To understand this, we have to take a deeper look into the system. In our system, the IMU triggers the camera captures, and depending on the exposure time, this can be different and is depending on the brightness of the scene. We define in the mid of these exposure times the timestamp for the image. So we want to estimate the camera pose exact at this time. In the background, while we capture images, the GNSS IMU positioning algorithm computes in real time the position and the attitude of the sensor. And we now use this positioning algorithm from GNSS IMU to estimate the first initial pose information for all of these images. So another representation is, can you see here now? So we have here a 3D coordinate system, for example, GS18 I, and now we have this image plane, and we know now the location and the orientation in this global reference frame. So now we can say, okay, we are now globally referenced our images. That's all that we need. That's true, but for our purpose, the quality of the camera pose information is not good enough to take measurements in centimeter level, in the centimeter level accuracy. So the accuracy that we get is good enough for the tilt compensation, but it's not for our purpose for visual positioning. So we have to improve the 6 values, the 6 degrees of freedom, the camera poses, with information that you get from images. And the improvement is done in a classical bundle adjustment. So what are information from images? It's our so-called features. So features are distinctive point in an image like corners or junction or just a single spot where the imaging algorithm says, okay, this is a stable point and I can drag this stable point from one frame, so from one image to the next one. In this animation, in this video, you see how our instrument sees the world today. You see here green features. These are stable features which can be dragged from one frame to the next one. And the red features are also features, so dominant points, but which cannot be found in other images. So we will throw the red features away, and just the green features we use then to improve the camera pose. So now we have images and an initial camera pose information from the GNSS IMU system. Here you also say we now extracted some features and dragged them from one frame to from one image to the next one. And you see already the features, they're establishing a geometric connection between the images. And this is now a system which we can adjust. This is done with a bundle adjustment, and the result is that we get optimized camera poses and the accuracy level is improved. So now I want to show some overall results from the accuracy tests, how accurate we can determine the camera pose. In the first table, you see the initial camera pose from the GNSS IMU system, and you see that in the position domain, we're about 2.5 centimeters, so we would say classical GNSS RTK position quality. And for the orientation, we get, for roll and pitch, about 0.2 degrees, and yaw we can estimate an average with about 1.4 degree. When we now look at the pose estimation after the bundle adjustment step, so when we included the image information, we see that in position domain we're the same, but what is striking now that for the orientation we can estimate now roll, pitch and yaw with 0.1 to 0.2 degree accuracy. And that is an improvement from 20 for roll, pitch 50, and for the yaw angle, so we can determine it with 90% better than the initial one. So the tracked features really helping us stabilizing the estimation of the camera pose. And this high precision camera pose information can now be used to measure points in images. So we use classical photogrammetric forward intersection to measure points in images. So here's just a short principle of the photogrammetric forward intersection. So we need images and their corresponding camera pose information, 01, 0, and 02. In this example, we want to measure 2 points, P10 and P20. The only thing that we need to know now is the exact location, the pixel coordinates of the object points in the image. When we have all the pixel coordinates in all the images of the same object point, we can use photogrammetric forward intersection to calculate the object point coordinates. The big advantage of the GS18I is now that because we directly estimate the camera pose information in a global reference frame, which is normally defined by RTK or the PPP, the smart link position. All of these object points that we measure within images are also georeferenced in the same frame. So no time-consuming coordinate transformation has to be done afterwards. Another part of measuring in images is to select the corresponding image coordinates of the object points in all images. So here we also wanted to support the surveyor to do the job faster. We included an algorithm called point matching, and with point matching, the surveyor just has to select in one image the point of interest. And the point matching algorithm automatically extract a patch and a matrix, a reference matrix around the selected point and searches in all other images along the epipolar line for the same pattern in the image. If this is found, we select the point with pixel accuracy, and we use this image then for the point measurement. So it is no manual point selection needed in all of the images. The object point is automatically found by the point matching algorithm. But of course, it is also a manual refinement by the user possible. So now we have the technique, and now I want to show some performance result of the GS18 I, so that you get a feeling about the expected quality of visual positioning. To demonstrate the accuracy, we measured with visual positioning thousands of object points. To get a realistic feeling, we measured totally different objects, like the concrete edge of a bench, or a surveying nail on the street, black and white markers, or some stone edges, window corners, also pipes. So all of these reference points have known coordinates in the millimeter level. Here you see now the result of all of these thousands of measurements. You see here, in average, the 3D quality of all of these measurements is between 3 and 4 centimeters. In average, we could determine the position of the object points in 2D with about 2 to 3 centimeters. When we have a look on the plot on the right side, you see that most of all of the thousands measurements fall between 2 and 5 centimeters 3D accuracy. So we can really say with this measurement system, we can achieve the same positioning quality as classical GNSS RTK. The performance test also showed that we get the best result when we take measurements between 2 and 10 meters. So camera to object distance. If we are too close, the images get a little bit blurry and the field of view is very limited. And if you're too far away, we lose details in the images, and it gets difficult to identify the objects which we're interested of. And the accuracy specification may not be achieved. Also, because the GS18 I includes now an optical sensor, the camera, we are now depending on the light conditions. So that's why the GS18 I might get problems if we face direct the sun or capture images in a very dark environment where the images have low contrast. Also, structureless objects like water or mirroring building, or waving objects like vegetation or moving water is difficult for GS18 I because the feature tracking gets problems here, because we cannot track the features from one frame to the next one. But in general, the results show that with visual positioning, we can measure, in the case if you determine the position of the camera pose with RTK, with about in 2D with 2 to 4 centimeters, in 3D 3 to 5 centimeters, and if we determine the position with SmartLink, the expected accuracy is about 4 to 6 centimeters and 5 to 7 centimeters in 3D. This brings me now to the end of my presentation. So here at Leica, we constantly pushing the boundaries to develop new solutions to solve the surveyor's problem. With the Leica GS18 I, we offer now a multi-sensor fusion technology also for the surveying market. Thank you for the time, and I'm looking forward for your question in the chat.